So here is our term symbol, okay, and let's walk through it. So up as a superscript on the left, we call that the multiplicity, 2s plus 1, and that gives us the spin state. And we're going to go to all three of these in more detail. The capital letter L, that's our main term, okay? And that gives us total orbital angular momentum quantum number, the total, okay? And then here's the J value, the value of the angular momentum quantum number. And so that's also total, okay? So we're going to go through these one at a time and how we construct them. And I like to compare this to electron configuration on crack. So this is basically electron configuration, but a little bit more difficult. But that's okay. You're chemists and you're senior chemistry majors. We can do this. So let's go. So the first thing that I want to talk about is the main term L. And what I'm going to point out, there's a couple different ways to come up with these term symbols. And most textbooks, of course, go through the super confusing way on how to do it. And that's called this Clebsch-Gordon series. But I'm going to provide an alternative method for coming up with these term symbols that I think works really, really well. So here's this alternative approach, but only if you know the electron configuration. And for ground states, that works just fine. This gets really difficult for excited states, okay? Getting the electron configuration of the excited state. But all the same, let's go for it. So we remember that lowercase l, this corresponds to any one electron. If it's 0, it's an S. If it's 1, it's a P. If it's a 2, it's a D, etc. Okay? The total L value, the capital L, the main term, is given by the Clebsch-Gordon series, which gives all possible values of L. And that goes as L1 plus L2, or plus L3 plus L4, etc., if we had more electrons. And then that goes all the way down to L minus 2, with possibilities of L plus 1, L plus 2 minus 1, and so on. And depending on the number that we get, if we get a total L, capital L, to be 0, we use a capital S. If we get L to be 1, we use a capital P, and then a capital D, and so on. So it mirrors the lowercase l. However, this is our total L value, and we use uppercase letters to indicate that. So for example, let's suppose we have a P2. And what I mean by P2, this is some system that has 2 p electrons. But we don't know where they are. We don't know if this is a ground state. We don't know if this is an excited state, and so forth. So what that means is, and here I'm drawing a picture of this, but we're just saying suppose that's what it looks like. So if we use the Clebsch-Gordon series, we note that both of these p electrons have L values of 1. Okay, so my big L is going to go 1 plus 1 is 2, but then I could go 1 plus 1 minus 1, that would give me a 1, and all the way down to L minus L, that would give me a 0. And so if I look at all of the possible terms, that's an S, a P, or a D. All of those term symbols are possible for any given P2. And so what I mean by that is it could be in this configuration here. It could be with 1 electron on the left, and we skip a block, and then we put 1 electron there. It could be with both of those electrons paired. S, P, or D could correspond to those, and we don't know which one it is unless we know the electron configuration. Okay? So here's the alternative approach. And let's see, I think I have that on the next slide. Yes. So the alternative approach is that capital L equals the absolute value of capital ML. And this capital ML is the sum of all of the ML values. So how do we get the correct ML values? Well, I certainly go through this in general chemistry, that there are actually specified ml values for a given orbital block. But if you didn't do that, here's some review. So S, all ml values are 0, okay? For P, and this goes in order of how we would list the electron configuration from the periodic table. For P, we start at -1, 0, +1, okay? For D, -2, -1, 0, +1, +2. And for F, right, you can see it, -3 all the way through +3. So now if I go back here for a second, and I suppose that this is in fact my P2 electron configuration, that I know that that's what it is. So we know now that those ML values are -1 and 0. And if I were to sum up those ML values, right, I'm going to have the absolute value of -1 plus 0 to give me 1. And if L equals 1, then I know it has to be a capital P term. All right? So what if the electron configuration, so I'll make a little key here. So if it looks like this, both up and both up, that gives me a P term. All right? Let's go through the other possibilities. What if it looked like this, where we skip a block? And of course, that would be an excited state, right? Well, we would have a, I'll finish labeling this, -1, 0, +1, all right? So this electron would be -1, and this electron would be +1. -1 plus +1 is 0, right? We don't take the absolute value until we do the final term at the end, okay? Oh, I labeled these incorrectly. Oh my gosh, you guys are probably looking at me like, what the heck, dude? Sorry, the L2 is a D and the L0 is an S, but I got the P right. Okay, my bad. So anyways, this term would end up being an S because the -1 and the +1 cancel to give us a 0. And so then our final possibility would be given by forcing these both to pair up. So then both would be -1, right? -1 plus -1 is -2. And the absolute value of -2 is 2. So that would be our D term. So you can see right away why this Clebsch-Gordon series is a little confusing. Because if we're saying, okay, we've got a P2, it could be a D, a P, or an S. Well, we don't know which one it is because we don't know what the electron configuration is. However, if you know the electron configuration, then you can ascribe what that P, S, and D term is to those particular arrangements. I hope that makes sense. Let's do another example. So here's carbon, 1s2, 2s2, 2p2, right? Same example that I just walked through. And if we do this by the ML examples, and I'll also show you that when I go to add up everything, right, especially with the S block, I've got 2 electrons in the S block here. So that's going to be a 0 plus a 0. And I've got 2 more S electrons in this 2s block, which is another 0 plus another 0. And then finally, here's my 2p. Right, and I remember that was -1 and 0. So that's plus -1 plus 0. And of course, all of that just equals 1, which was our main P term right here, right? So we're just going to use the letter P. And so what's important to note here, we can often ignore the core electrons, the closed shells and closed subshells. Because you note that they all, especially if it's S, right, they're all going to cancel out. So we can often just look at the valence electrons to get the correct term symbol. All right? Okay, so let's move on to the next terms.